Today's topic is astrophotography. This has been something that's been a real passion for me since my retirement in 2019. So I'm happy to join you today and talk a little bit about what takes up most of my free time. So it's fairly interesting today with the technology that's available to almost anybody who's willing to pursue it. You can capture images from your driveway that can challenge those produced by some of the professional observatories in the past that had massive telescopes. It's possible, but it's not very easy. There's a huge learning curve and there's a lot of technique which has to be mastered. My goal today is to share with you what it takes to create an image from the deep sky and explore a little bit what it takes to make a great image. Astrophotography is a huge topic, and this talk will be both a little shallow and pretty wide. There's just too much you could get into here that I just won't have time to do. But if you're interested, there are a lot more details on my website, cosgrovecosmos.com, and my YouTube channel. I tend to share all of my projects and talk about how I do my processing and how I set up my equipment so that others can learn from some of the things that I'm doing. So let me talk a little bit about myself for a second. I have a background in image science and consumer imaging systems. I spent 32 years in Eastman Kodak research labs before that organization went into the dustbin of history. But I had a really enjoyable career there. But even then, I had a very long-term interest in astronomy. It started when I was really a boy. And in the 80s and 90s, I was very involved with visual astronomy, and I tried to do a little bit of film-based astrophotography, although that didn't go too well. And for a long time there, I was a very active member of the astronomy section of the Rochester Academy of Science, which is our local organization for such enthusiasts. And then there was this 30-year hiatus. In 1 year, I got a promotion at work, which took on a lot more responsibility. We built a house. I went back to school for a grad degree, and we started a family. Suddenly, there wasn't any time for anything other than those activities, and it sort of went by the wayside. But I knew I wanted to come back to it. It was something I had a deep interest in, and in my mind, I thought I would come back to it when I really had the time to devote to it. And I figured that would happen when I retired, and that happened in 2019. And within 30 days of my retirement, I had my first astrophoto rig, and I was trying to figure out how to put it together. Back 30 years ago, when I tried to do astrophotography, it was film-based. Back then, I was using Kodak TechPan 2415 film, which was a technical black and white film that was very fine-grained. And we would have to do something with that film to make it more useful for astrophotography. We would gas hyper it. And in gas hypering, you take your film and you put it in this chamber over here. And this chamber you would draw a vacuum onto, and then you would heat it up with resist wire, which is wrapped around the outside of it. And that would drive moisture that was in the emulsion out. And the goal here was to handle some of the reciprocity failure that happened with the film. So we would get rid of the moisture, and that would help. And after a while, when we thought we had the moisture out, you'd backfill it under pressure with a gas that was a mix of nitrogen and hydrogen. And this would sort of pre-expose some of the silver halide crystals so that it wouldn't take a lot of photons to make them trip and make them much more sensitive. But once you spent about a week preparing your film, you then froze it until you were ready to use it. You thawed it out. You then had to start setting up your equipment. Back then, it was pretty hard to achieve focus when you put a regular film camera onto a big telescope. We dealt with very long exposure, between 2 and 6 hours for a single frame of film. And during that time, if a plane or a satellite happened to go across your frame was ruined and you just started over. We used to do manual tracking. We had a secondary telescope on the main telescope. It had an eyepiece with crosshairs on it, and you would line it up with a star, and you'd watch that. You'd sit there for 4 to 6 hours, and if that star moved off the crosshair, you had manual paddles that you would use to bring it back online so that the tracking was pure enough that you get a good image on the film. Then, of course, we had to process the film and print it before we could see what we had. And typically, when I went through this process, the results I got were pretty bad. It really wasn't something I enjoyed. So I did mostly visual astronomy back then. 30 years later, I started to look at what was going on. It was a whole different world. We had computerized go-to telescope mounts. We had this thing called plate solving, that when a telescope looked at a part of the sky and it thought it knew what it was looking at, it would take a picture, and then the computer would figure out what you're really looking at and create a model that would correct for the pointing so that you had very accurate pointing. Instead of 4 to 6 hour exposures in one piece of film, we tend to do many short exposures, between maybe 30 seconds up to 5 minutes. And then all of those exposures are stacked together through software. Focus and guiding are completely automated now. The capture is controlled by computer and is automated. And the processing is digital. And we have very sophisticated tools we can use to try to maximize the signal we're trying to get. In short, I found a whole new world. And since my background was in image science, I was like a kid in a candy shop. I knew I was going to have a lot of fun with this. And I thought that my years of doing digital imaging research for the consumer market would be a big help. And I found that wasn't quite as true as I thought. Normally with images we deal with everyday cameras, we have plenty of signal. And the question is trying to get the most pleasing image. But in this case, we had so little signal. The real issue is trying to tease that signal from the background noise. And the methods there are very different than what you would do with in normal photography. So I had an awful lot I had to learn. Let me talk about the kinds of imaging I do versus the kinds of imaging I do not do. I do deep sky imaging, and basically this takes two forms. Basically, it's nebulae and clusters from our own galaxy, and I have two samples here. First is the Great Orion Nebula, and the second is the Elephant Trunk. These are inside of our galaxy. So basically what I'm often looking at is clusters of stars, areas of dust and gas that are excited. And these are areas of new star formation. So they glow, and they glow in beautiful colors, and they can be quite large and they can be quite small. The other thing I take pictures of is other galaxies. When you're looking towards the Milky Way at night, you tend to see images that look like this. When you're looking away from the Milky Way, you can't see our galaxy, you start to see other galaxies. And the closest one is 2.5 million light years away. Many of them are between 50 and 100 million light years away. So it's pretty interesting to try to capture these things because the photons have been traveling for millions of years before they happen to hit your camera sensor. And so that's kind of an interesting thought. So all these are characterized by very faint subjects that are very far away. Now, there's other forms of astrophotography that people get really involved in. Solar photography, lunar photography, planetary photography, comet photography, when there's a good comet is a big one. Capturing the aurora at night, meteor photography, large-scale images of the night sky as the Earth rotates. A lot of these are really focused on things that are inside of our solar system. They have very different methods and equipment from what I use. I haven't delved there. I don't do that. I pretty much stick to the deep sky because I kind of like the idea of capturing those things that are so far away. And I also do almost exclusive color imaging. And when I do color imaging, there's two kinds of color imaging. One is just RGB color imaging. It's basically doing a camera color of the way most cameras would work, and it's sort of mimicking what the human eye could see if you could see very faint objects. But I also do narrowband imaging, and this is something that creates what I would call false color. Basically, these are very, very tight, narrow cuts in the spectrum that line up with the specific areas where gaseous clouds that exist in space can be excited by nearby stars, and they emit light in a very narrow frequency band. And with these sharp cut filters, you can get amazing detail in the patterns of these various molecular clouds, but they're not red, green, and blue. But you want to represent them as a color image we can look at. So we put them together into a kind of a false color, and they can be dramatic and impressive, but there's really no correspondence with reality at that point. It's just a way of representing the interesting data you collected that way. So what makes deep sky imaging hard? What's the challenge here? Well, First problem is the targets can either be very small or very large, but they're all very faint. Just to give you a little bit of a feel for that, most people are probably familiar with how large the full moon seems to be in the sky. It's about half a degree in angular size. One object I have over here is Messier 27, known as the Dumbbell Nebula. Just as a comparison, this is about 5 times smaller than the full moon. So it's not super tiny, but it's not large either. But it's 4 million times fainter. So capturing it has very different technical challenges than what the moon does. Conversely, we can talk about Messier 31, the famous Andromeda galaxy. It's the closest galaxy to our galaxy. And it's bright enough that if you were in a very, very dark sky site, you could just barely detect it with human vision. That's about 6 times the size of the full moon. It's large. It's really big up there, but it's 2.5 million times fainter. So what we have to go over, sometimes we're looking at very small and faint things, and other times we have fairly large things. And sometimes I go after gaseous clouds, which can be even bigger than this. So a lot of times you think about astrophotography as objects that are very, very far away, and you tend to think they're small, but that's not necessarily true. They are faint, though. The other problem is, as you're trying to go after these faint things where you need longer exposures, the Earth turns and tends to move it outside your field of view very quickly. So that's kind of a problem, and you're going to have to deal with that. The other problem is the night isn't always dark. You know, if the full moon is out, it illuminates the background sky to the point where it can wash out these very faint objects. It's not always clear. You know, I live in Rochester, New York, and I imagine my weather is pretty similar to yours. We have quite a bit of cloudiness and not that many clear nights. And things that we also have been dealing with over the last few years is smoke plumes from forest fires that are coming from Canada or out west. And during the summer, we have to watch where the smoke goes because that obscures our view. The other problem is the most pleasant time of year to be doing this is in the summertime when it's nice and warm, but the nights are actually quite short then. You only get about 4 hours of true darkness compared to the fall where you might get 10 or 11. So your night always doesn't cooperate, and you have to get your timing down in order to be able to do what you want to do. The other problem is that no matter what time of year it is, as you start out, you have one temperature. In general, the night gets colder as time goes on. And why is that a problem? Well, it causes the metal in the telescope to contract a little bit. It shrinks its dimensions. And when you have very critical focus going on, it'll throw your focus off, and you're going to have to deal with that. The other thing is now that you have colder metal, you tend to hit the dew point at some point, and you'll have dew forming on your optics. And that's another challenge you're going to have to work through. So there's a lot of things in here that conspire to make this a little bit challenging. So how do we deal with those challenges? Well, basically, some of this is having good planning. Some of this is having gear that's set up and built to deal with the challenges you're going after. Some of it today is you're really using pretty sophisticated software to automate things and precise methodologies so your equipment is set up and working the way you need it to work. And finally, now that we're in the digital age, there's some unique image processing that really allows you to work on these images and really make beautiful images from very, very thin signals that you've captured. Let's talk about what the key enablers are for astrophotography. I would say one of the biggest is you have to have a pretty strong interest. And the interest has to be there and the drive has to be there because there's a lot to learn and you have to be very good at technical problem solving. You have lots of systems you're going to be bringing together, and if for some reason they're not playing well together, you're going to have to suss out what caused that problem. You're also going to need at least a few dollars because you need the specialized equipment that lets you play this game. So that's another enabler. Access to the sky is pretty critical, and you'd think that would be obvious, but you know, there's a lot of people who live in the city, and the light pollution there makes it very difficult for them to pursue their pastime there. That means they have to travel when they do this. Other people, like myself, the area where I did most of my astrophotography until recently had a lot of trees on the property. So I had narrow slices of the sky that I could actually see between the trees. So access to the sky is something that's pretty critical, and it isn't always something you can take for granted. It's also pretty handy to have a supportive spouse because if you're going to do things like this, you'll find yourself up late at night and sleeping during the day, and it's pretty good to have someone that's tolerant of that. But I think the biggest driver on this is time. These projects take a lot of time, and I knew that, and that's one of the reasons I waited till I retired. Just to give you an idea of what it looks like when I do a typical project, just planning alone can take me 2 hours choosing the target, trying to figure out what's going to be in the night sky that would be a good thing to image, determining how I want to image it, getting all that planned out can take me over 2.5 hours or so. Then, because I shoot from my driveway, I have to set up my equipment in the beginning of the night, and then at the end of the night, I have to take it down. When I first did that, it used to take me like 3 hours, but I've gotten quite good at it. Now I can get it down to about an hour and a half a night. But that's time you have to spend, and you have to do it each time very precisely if you want to get consistent results. Then when you're capturing an image, to get enough data to get the quality I want, I might have to capture it between 3 and 5 nights. At 3 and 5 nights, I'm staying up, babysitting the equipment to make sure that I'm getting the data that I want. Once I have the data, I have to process that data. And there's so much of it, and it's so compute intensive, it can take me between 1 and 3 days to get the final image that I'd really like to have. Then, because I have a website, and one of the things I do, when I was trying to learn this stuff, I often had difficulty finding guidance for how to go about this. So when I created my website, I decided that every time I did an imaging project, I was going to write up the whole project. I was going to talk about everything from how I chose the targets, how I set up the gear, the problems I ran into, and how I solved them. And then when it came to processing, I actually showed a step-by-step augmented view of how each step I did to process those images, so others can look at that and get ideas from it. There are people who offer this now, but they're behind a paywall, and I decided I didn't want to do that. I just wanted to share that information. But that takes me another 2 or 3 days to document all that. So one project here can take 11 days, and I'm running 3 telescopes. So over a span of a few nights of good weather, I've got a month's worth of work that I'm going to be doing there to really pull this through. So time is a huge enabler for this kind of pastime. How I started, I said after 30 days, I had my first telescope. And this was the first telescope that I got. And my wife knew that I was going to be getting involved in this, and I was doing research on it. And I sort of knew what I wanted to buy, but there were some technical issues I didn't understand. So I mentioned to her I was going to call one of the local suppliers that had a tech support line and just ask them questions. And they were very good. They answered my questions. And this was 2019, and quite often the supply chain was problematic. So I was just asking, how hard is it to get these things right now? And they're saying, yeah, it's been really, really tough. But, this telescope you're interested in, I have one here right now that's not spoken for. And this mount, we haven't seen them for a quarter, but we've got a shipment coming in next week. And I still got one more that I have orders for. If you want, you could put your name on this now and you have it. So I took out my credit card and I bought this equipment. And that was very easy to do. I had to go back and explain to my wife that I just spent $5,000 without getting her approval. That wasn't so easy to do. But I did have my first telescope, and what I ended up getting was a 132 millimeter f7 optical system by Williams Optics, and this is a refractor, an APO, color corrected refractor. I had a small telescope for guiding and tracking, and that was just a 50 millimeter diameter scope. I ended up getting a dedicated camera that had a Bayer pattern on it, so it'd be color cameras. And basically, the sensors are very, very similar to what you would have in the cameras you use every day. It's just that this camera is built purposely for astrophotography, and it has a cooling capability in it to cut down some of the noise of what goes on. There's another camera right here which attaches to the tracker, and that helps the telescope mount make sure that it's pointing where it really needs to go. Then finally, I got a heavy-duty mount that let me track the sky as the Earth turned. And it would handle a 60-pound load, and the telescope weighs about 30 pounds, so I'm in pretty good shape. But I had something I could start to play with. So I got started. First, I had a lot to figure out, just how to plug everything together and how to get the software connected and make it work. In the daytime, I got things connected and working, and I could see things through the camera. So I looked at distant treetops and got a rough focus dialed in. After dark, I learned how to align the mount to the pole star so that it rotated the way the sky rotated. Then I used the go-to feature on the mount to go to what I knew was a very bright nebulae that was in the summer sky towards the south, Messier 8. And I commanded it to go there. And then using some very simple software, I told it to go off and make a 60-second exposure of that. Nothing happened for 60 seconds. Then suddenly this popped up on my screen. This is some free software that I got at the time that would allow you to do minimal control of your telescope. And in this case, I told it to take one frame for 60 seconds. And I was a little dumbfounded by what I saw because I'd looked at this object many, many times in relatively large telescopes. And I didn't see as much detail as I could see in this image. And this is the actual image. I took a picture of it with my cell phone. I was so excited. I instantly texted it to my family and friends because I was so impressed by it. And apparently I was the only one that was impressed by it. But for me, it was a pivotal moment. So then I told the software, instead of taking one of those, go back and get like 14 of them. So here is my very first image that I ever made. Again, this is Messier 8, the Lagoon Nebula. This is the result of 14 60-second exposures stacked together. I got some free software that let me stack it together. Objectively, this is a bad image. The stars are out of focus. The stars are blown out and have no detail. They're just little cookie cutters. I didn't do any guiding yet because I didn't know how. I did no calibration of the data because I didn't know how. This was a color camera, but I had a neutral image. Where's my color? Well, at that point, I didn't even know that when you get a raw image, it hasn't been debayered yet, right? So it hasn't created the color. So I'm actually just processing raw pixels and I lost my color. So this is an objectively bad image, but you know what? I was completely and absolutely hooked with this image because in this bad image, I saw more details of these dark rifts than I'd ever seen in a telescope. I could see these little dark nodules in here, which are dust clouds that are coalescing under their own gravity and will soon form their stars that are going to be born from that. It was fascinating that I could get that level of detail out of something in my driveway, and I really wanted to get going and do more of it. So I did. Here are some of my early images taken in that first month. Messier 57, the Ring Nebula. This is a planetary nebula, a star that has shed its outer layers, and you can see the shape of the ring there. Then this is part of the Veil Nebula and Cygnus. It's called the Witch's Broom, this sequence. And you can see this little stream of gas and dust and a bright star that's illuminating it. This is Messier 16, the Eagle Nebula, and the Hubble telescope had a famous image showing the pillars of creation in here. That's a very famous image. Well, I can't see much of the detail there, but I could see the pillars of creation. And again, that's something I did with my own hands, and that was pretty exciting. Then I took a picture of the Crescent Nebula, which is another planetary nebula where this central star right here shed its outer layers, and I could actually see the different layers, and I was actually picking up some colors when I was shooting with red, green, and blue. Now, these are still really bad images. They're bad images because all the background is clipped to black, excuse me. All the stars are clipped to white. The backgrounds all have different colors, and I was using Photoshop and didn't know how to process these images appropriately. So they're kind of crude and they're not as good as they could be. It didn't matter. I had data coming through my telescope. I was learning. These images were now in color. These images had some early calibration frames applied, and I was starting to get my technique tuned. And I kept working on it. Every free night I was outside. My bad images started to become good images, and my good images. My first image of the Ring Nebula, about a year later, I produced this image. This image is a combination of red, green, and blue data, which shows much more detail on the ring itself. And you can see the central star that was the source of this outgassing. But I also put some narrowband filters in, and I put a narrowband filter in that would bring out the hydrogen gas that was around it. And I found these interesting series of shells of different levels of hydrogen gas that were being blown away from the star. And it looks kind of like a rose, and I thought that was pretty amazing. The other thing I was able to show is that look at this little barred spiral galaxy up there. Normally, when you're looking in towards the Milky Way to see this kind of thing, you don't see galaxies because galaxies are in the orthogonal direction off to the side. But every once in a while, you get to the edge of the galaxy, you can pick up our galaxy. You can actually see some other galaxies. So this is one of those rare photos where we have a big object from our galaxy along with another galaxy that happens to be in the background. I went back to the Witch's Broom and tried it again about a year later, and I got much nicer stars. Notice the stars aren't blown out anymore. They have color of their own, picking up real shimmering light detail in this gas. And all these little bright arcs are little pressure fronts in the gas from stars behind it driving it outward. And I thought it would look really delicate and beautiful. My original image of the M16, I shot again, this time in narrowband. And the level of detail I was able to capture and the beautiful color that you can get with narrowband really jumped out. And suddenly the pillars of creation look a lot closer to Hubble than I thought I would get with a 6-inch telescope in my backyard. This image has been used for the jersey of a professional soccer team on the west coast of the US, and was recently used in a Apple 3D headset, the Vision Pro. They created a space experience using that and in augmented reality, and they used my image in here for that particular production. My Crescent Nebula, I went back and did a narrowband study of, and I was amazed what I saw there. I did this with narrowband, so the hydrogen alpha comes out as red in here, and all this beautiful red gaseous clouds that I couldn't even see before. And then the texture of the gases, they're so dense around the, expanding around the star, they almost look like a human brain sitting there. Then this light green, this teal colored part is from oxygen 3. And it's interesting to see how there's almost these convection cells that are boiling off the gas in a thin shell around this whole thing expanding. So it's always fascinating when you get this. You don't really know what level of detail you might achieve. And sometimes you're just, you're trying to learn what you're looking at after the fact. So this was my first image. About a few months later, I tried again, and I did this and got my color out, and I got a much better version of it. But astrophotographers tend to go through kind of this common journey. You got to get your gear, you get it together, and you get your first images. And I'll tell you, a lot of people don't get this far. They can't figure out how to get everything to play well together. And if you get to the point where you're making any image, no matter how bad, it's kind of an accomplishment. You should feel good about that. But once you get your first images, then you start working to improve your technique so you maximize the quality of your captured data. And you'll quickly find that the data gets better over time, but after about 6 months or a year, it sort of plateaus where you've gotten competent enough to get solid data. There isn't a lot more you can get by improving your technique there. That opens the door to another area where there's no end to the learning curve, and that's the image processing. The image processing is quite complex, and there's many techniques, and learning all of them and knowing when to use them for what situations, that can take years and years and years. I've been doing this now for almost 6 years, and I still feel like I'm scratching the surface of that. And this is one of those big areas that really changes the quality of your final image. And that's a personal skill. And every astrophotographer not only has their own skill that they develop there, but you develop this thing I call your inner eye. As you work with this data, you start getting an idea of how you want to represent this data, how you think your data should be represented, and how you do your processing. When you stretch the contrast, how far do you stretch it compared to someone else? You develop almost a signature look, and almost every astrophotographer has that. And really great astrophotographers are really good at this, and they develop wonderful renditions that are consistently good. So I thought, just talking about in general, I would share with you a half dozen of some of my images just to show you the things that I get excited about. And then what we'll do is we'll take one of those images and I'll walk you through what it took to create that image, some of the steps involved, so you get a better appreciation for that. So this is a Wizard Nebula. It's in the constellation of Cepheus, and it's 7,200 light years away. This is 12.5 hours of data. Some of it is narrowband data. Most of the clouds in here are narrowband, but the stars I took from red, green, and blue data, so that the color of the stars is actually pretty accurate. And this is the first image where I did that and combined them back together. And this is kind of a Rorschach thing, right? You have all these clouds in space, and some of them seem to take on certain figures. So here we have our wizard with his nose and his eyes and his pointed cap and his hands doing some incantation or something. But this is a pretty well-known target, and one that everyone who does this has to visit at some point or another. This is the Rosette Nebula. It's in the constellation of Monoceros. It's about 5,000 light years away. It's a very large object, and it spilled over the field of view of my telescope. So I sort of centered on the core here. It's kind of like a donut where there's a thinner area in the inside, and on the outside, there's gas, but there's also a lot of dark dust and whatnot. This was a relatively short exposure, about 3.3 hours in narrowband. And this one I'm very proud of because it's the first image I ever had published. This was published in Astronomy magazine, the January 2022 issue. And so after doing this for a few years to get your first image published, if that feels very good. This is the North American Nebula. This is 9.3 hours in narrowband, and it gets its name because this area in here kind of looks like the continent of North America, and this is the Gulf of Mexico. It's not the Gulf of America, it's the Gulf of Mexico. And you can also see across the way here, this is the Pelican Nebula over in here. So there's the eye of the pelican, and there's his beak. His neck comes down here, and then here's his body and his wings. This particular image was about 10 hours of narrowband, and it was the first image I had published in Sky and Telescope magazine. And as a matter of fact, they printed it as a 2-page spread. And Sky and Telescope is kind of interesting. They're very difficult to get your images into Sky and Telescope, but they don't necessarily tell you that they're going to use your images. The other ones do, they don't. And one day I had an issue show up and I was flipping through it and I opened up, it had this big centerfold and it looked familiar, and that was kind of a shock. So again, that's part of the things that makes you feel good when you're doing this kind of thing, is it seeing other people think enough of it that they're willing to publish it. This is the Elephant Nebula. This is in the constellation of Cepheus, and this is 2,400 light years away, and it's about 7 hours of exposure data in narrowband to create this. This was published in Amateur Astronomy magazine, issue 106, back in November of 2022. This is part of the Veil Nebula in Cygnus, but they call this particular portion the Bat Nebula. And you can kind of see the head of the bat with his ears here and his wings outstretched. It's a fascinating area of expanding gases and dust. And you have such delicate patterns that you can find throughout here that it's just amazing you can get lost in looking at it. This is another planetary nebula where a star has shed its outer layers. This is the Helix Nebula, NGC 7293. Kind of close compared to some of the other ones. It's only about 700 light years away in the constellation of Aquarius. This was 4 hours and 38 minutes. And what I like about this one is you can really get a sense that this is blowing up away from the star. You can see these linear striations of material, fine material, that are all pointing back to the star. And that's the only planetary nebula that I've taken that I've seen that particular pattern on. This is the Tulip Nebula in the constellation of Cepheus. It's 10,000 light years away. This is a rich area of star formation with lots of dust and a lot of gases that are coalescing and creating new stars. This is a big area of star formation in this ridge here. This is the tulip itself. And this image was about almost 13 hours of exposure. And in Rochester, New York, 13 hours is really hard to get for an image. So I was happy I was able to get that much. And when I shared this image, one person came back and he said, wow, this is a really nice image. You did a great job. You even captured the shock wave, the bow wave in the image. Good work. And I said, well, thanks very much. And I had no idea what he was talking about. But so I did some research, and what he's talking about is this little arc of material right here. It turns out this is actually kind of a famous thing in the sky, and I didn't even know it. There's two stars down here. This star down in here has a dark companion. That dark companion is Cygnus X1. It's the first black hole that ever was confirmed. We knew there were black holes based on theory. We never actually found proof of the existence of one until this particular one. And the event which caused the formation of the black hole sent a shock wave out, and this is a huge shock wave, which is quite far from the star now, but that's like the leading edge of it. I captured it in the image and didn't even know it I had. And so one of the things I learned in doing this is that not only when you're done capturing, you look at what you captured, now you can research what else is in your image. You pulled up your fishing net and you don't always know what you might find, and that is like a little act of personal discovery each time. This is the Andromeda galaxy. We were talking about this being the six times larger than the full moon. This is about the third time I think I particularly shot this one. This is in the constellation of Andromeda. It's 2.5 million light years away. It's a result of 6 hours of exposure. And this one of the things I thought made it a little bit interesting is instead of just doing red, green, and blue, I also captured the narrowband hydrogen alpha channel. In that case, it kind of shows the areas of star formation. And if you look around the edge here, all these little pink nodules, these are areas of rapid star formation that are shown in the hydrogen data, and I was able to fold that into this particular image. The Webb Deep Sky Society back in 2022 named this as their picture of the month. One of the objects that you can photograph are globular clusters. These don't have any gas or dust. They're just massive accumulations of stars in a very high density. And these tend to circle the core of the galaxy in orbits. And the largest and most impressive one in our skies, Messier 13, which is called the Great Hercules Cluster. About the time this was becoming well positioned, I was trying to improve my technique to maximize the sharpness of my images. And I used this as a test case. And I was pretty happy that I got the resolution that I did. I was pretty happy that I got pretty good color in all the stars here. But what also made me happy is when you take a picture of this, quite often there's another galaxy off to the corner here, and it's usually just a white smudge. And when I looked at it here, I actually could see some detail in it. I thought that was interesting. But then I noticed there was another little tiny edge-on galaxy I'd never seen before right in here. So I thought, well, that's interesting. Let's zoom in and take a look at that. Here's the large galaxy, and I was amazed that you can see a spiral structure to it. You can see the orange glow of the old generation stars at the core and the cooler stars at the edge. You can see dust bands that make up the arm. I just never expected that I was going to get any kind of detail from that tiny galaxy, but I was able to resolve some of that, and I found that fascinating. And that little tiny one I looked at, I figured, well, that's just going to be a smudge. But actually, if you look at this kind of squint, you can also see the orange of the old central stars. You can kind of see a little bit of a hint of spiral arms. So there was more data there, or more structure there than I would have imagined. Even though this is getting right down to the pixel level, it's starting to pull out some of that detail. So that I thought was interesting. And it also told me that what I was trying to do to improve my spatial techniques was working. This is the Sunflower Galaxy. It's 27 million light years away in the constellation of Canis Venatici. And this was the first one that I took with a new generation camera that came out maybe 2 years ago, where the quantum efficiency of the sensor was 90%. So very, very efficient. And the level of detail and color I was able to pull out for this spiral galaxy was pretty impressive. I shot this before and there wasn't anything like that. So here's a case where, you know, as your sensors get better, your ability to pull in that detail gets better as well. This is about 10 hours worth of data in RGB broadband and hydrogen narrowband. This is one I took about a year or so ago. It's a Wolfert-Rayford star, which is a very high output star region in Cygnus. This was a result of 15 hours worth of data. And I found it kind of fascinating, these huge star fields of gold and blue. And I shared this with some friends, and one came back and said, you're doing this wrong. You got this set up wrong. This is the way you should be showing it because there's a face in that cloud. You can see the face there. There's the eyes here and a little bit of hair on the top. So amongst our local group, we're talking about, we're calling this the face. This is one I took last year. It's the question mark nebula, but it's the central portion of the nebula. 14 hours in both narrowband and RGB for the stars. And I just found this to be a really interesting area of space with a lot of detail, a lot of color, and a lot of dark nebulae. All of these are coalescing dark dust clouds that are going to shrink in on themselves and form stars someday. So that gives you a little bit of flavor of the kind of images that I try to take. But I should mention that I also have developed an ethos around my images. And the ethos can be summarized by the word my. And I'll explain what I mean by that. When I do this, the data that I'm using is data I collect myself. And the reason I bring that out is there are people doing astrophotography where they're taking data from the Webb telescope, the Hubble telescope, the public domain, or they're taking it from someone else. They process it and then they put it out there and say it's their image. So, you know, that doesn't sound right to me. I think if you're going to do this, you do it with your data. It's collected with my gear. My data is collected with my gear. That means it's my telescope platform that gathered the photons. It's equipment that I selected, assembled, and configured myself. And I say this because there are telescopes out there that you can rent. I saw an impressive image the other day, and it turned out it was a 24-inch telescope in an observatory in Chile that a gentleman had booked for an evening and paid for. And they had the technicians there collect the data. And I'm thinking, well, no wonder it's a wonderful image, but you're using a professional telescope collected by professionals, and then you're passing this as your image. And I thought, that's not what I want to be about. I want to set this telescope up myself. I want to plunk it out in the driveway. I want to do the alignments. I want to get all the gear. I want to make sure that what data is collected is because of the way I set it up. The processing, I do all the processing of the image myself. I make all the processing decisions, and the final look of the image represents my vision for a particular project. And I say that because there are some folks that work in teams, and one person collects the data and another person does the processing. And it's a team effort, but if you're going to represent it as your effort, you really didn't do all the work, right? You shared the work. And so in my mind, it seems like my ethos, I want to make sure I did it myself. Another thing I'll bring up is that in the astrophoto community, there's quite a bit of controversy right now going around the use of new advanced AI tools. There's one group that thinks using AI tools is evil and isn't really representing the data you collected. And then there's another group that says, hey, it's a great tool. It helps me do my work. Why can't I use it? I have a little bit finer grained take on that. When it comes to AI tools, there's two kinds. There's some that are called discriminative, and there's some that are called generative. Discriminative ones take the data you have and under your guidance enhances that data in some way. A generative AI tool will make an amazing looking image, but it changes the data. You might have a great picture of what you think is the Andromeda galaxy. It looks impressive, but if you look at it, the details are all different. The stars aren't where the stars were. The gas structures aren't where the gas structures. The AI built a pleasing looking astrophoto, but it has nothing to do with the data you collected in objective reality. So for me, I use discriminative tools, which are powerful things that let me shape my data the way I want, but I'll never use generative tools because that's just painting. That's just animation. It has nothing to do with the art of photography at that point. So in my mind, if you break these rules and you create a great image, does it really count? Is it really yours? And my take on that is no, it isn't. So let's look at what goes into creating such an image. And for that, I'm going to go back to the dumbbell nebula we talked about before. And this picture was one of my early pictures of the dumbbell. And, this is pretty typical of what you'd see in a telescope view even, except you wouldn't see the color. You see kind of this hourglass wasted shape. This would be a dark void here, and this would be a dark void there. And, it's very popular thing to visit with telescopes because it's pretty bright and you can see it quite well. It's also known as the apple core nebula because it looks like an apple core where someone took a bite on each side. NGC 6853 is its formal designation. And again, it's another planetary nebula. It's located about 1,200 light years away from us in the constellation of Vulpecula. Again, we talked about planetary nebula are expanding shells of ionized gas ejected from red giant stars in the last stages of their life. And this one was the first planetary nebula ever discovered and documented by Charles Messier, thus the Messier 27. Now, if you look at that, there's about 100 objects that Charles Messier documented. And today we see it as kind of like the crown jewels of what's in the sky. You go down his list and you see these big, bright things that are great to look at in telescope. So you might think that Charles Messier was building a list of sights to be seen, but that's not really what he was doing. Back in that time frame, they were crazy about comets. They thought it had portents of the future and things like that. And they're all trying to discover more comets. And when you scan the sky looking for comets, you look for fuzzy objects that would move night after night. And every once in a while, they came across a fuzzy object like this particular object, but it didn't move night after night. And they realized it wasn't a comet, it was kind of a false signal. So Charles Messier created his list of these are not comets, don't be fooled by them list. So it was, basically things that were working against what they wanted. It wasn't a nice set of objects to go visit. It's kind of morphed into that over the years. We know because we have pictures of this taken many, many years ago that this is expanding. And if we go backwards in time, we know this star began shedding its outer layers about 10,000 years ago. So when you're going to do an image, it's good to have an idea of what you're trying to achieve. And so I wanted to do a unique take on this. Um, as I said, it's a well-known object with that familiar dumbbell look, but I've seen a few older narrowband images, and here's one that was taken back in 2010 that sort of suggested there was this shell of gas around the outside that was much larger than the object you normally saw. And that intrigued me, and I wondered if I could go after that and really emphasize collecting the data necessary to show that better. So that was what I set out as my goal to do, and I shot it in narrowband so I could get the molecular gas clouds that were there. And I was going to go for a really long integration. I want to go for like 20 hours or something like that. That was my plan. This was in August of that year, and M27 is in the constellation of Abecula, which is a very boring constellation. The asterism for it is just a straight line between two stars, so nothing to get too excited about. But it is sandwiched between Cygnus, the Northern Cross, and Aquila, the Eagle. So it's not that hard to find in the sky, and it's well presented in August. So, well, very good. It gave me a chance to hydrate as well. Okay. So we were talking about planning and other considerations that we want to get into. Um, you need dark skies, and I was talking about the fact that for me, that means when the moon isn't around, because when the moon's around, it's too bright and it messes up those faint objects. So, I would typically try to shoot for maybe between a time like in here to a time down in here. So there's about a week during the new moon where I could probably get some decent imaging done. And so hopefully, uh, I get uh, decent decent times then. And then in the summertime, like I say, I only get 4 hours. This is the time of year. This is the number of hours of true darkness. During the July, you're down to 4 hours. You can in the fall, you can go up quite a bit more. And I love the fall because of that. So you have to be careful to make sure you're collecting data as soon as it's dark and stop before it gets too light and maximize your use of that time. And then you need clear skies. And every astrophotographer I know has subscriptions to all kinds of weather prediction and sky prediction apps. This one's called Astropheric, which does a very nice job. This is my location in New York State, and I can look at satellite maps of projected cloud patterns and when it's going to be clear. This app also has satellite views and predictive views of smoke plumes. So that becomes something that's really important to be able to go after. And then when you're out on the driveway, you have to watch winds. If you have a lot of high winds, it rattles the scope because they're unprotected from the wind and you're not going to get good imaging anyway. So a lot of forces have to come together so that you have the opportunity to collect images. We don't have as many as I would like here. I have friends that are in like New Mexico and desert mountain communities where they have 300 clear nights a year. I don't think we have that in 10 years. So, that's a local challenge that we need to deal with, and we constantly are looking for figuring out when we can take advantage of a clear night. And smoke I already talked about. Another part of the planning process is composition. Most astrophotographers, when they start, they go say this is the Tulip Nebula. You can, in your automation software, you can pull up a plate survey done by professional observatories, and you can see your object and you can do some playing around. Most people say I want to point right at that, put it right in the center. But I found that it's much better to do some composition of the image to make it more dramatic. Just like images you would take of any kind of scene, you want to get the compositional elements looking right. So these apps allow you to drop in a square which represents the field to be covered by your camera through your telescope. And you can move this around in X and Y, and you can rotate it so you get what you think is the best composition. First year, I never bothered doing that, and afterwards I did, and I was always happy that I did because I thought it really improved the how pleasing my final images were. So that's something that we plan goes into that planning cycle, and once we've got that, it's captured and it's baked into the automation that we'll be doing later when we start the capture process. So let's talk about the place. This is not my observatory. This is where I took those images. This is my driveway. I'm facing south, and I have trees on one side of the driveway and trees on this side of the driveway. So I don't have really wide open skies. I basically wait for an object to send beyond the trees. I start shooting until it ends in the trees here. So that was a somewhat narrow window I had to deal with. When I face the north, fortunately, I have a gap in the trees where the star Polaris is. That's the pole star, so that's the star you need to calibrate how you align your mounts up to. Now, as it turns out, this hole wasn't naturally occurring. I had a couple of guys hanging from ropes with saws cutting out limbs so that I could get a view of this, because if you're going to set up in the driveway every night, having a sight of that star is pretty critical to being able to set things up right. And just for full transparency, this is not an actual image of the star Polaris. It's just an incredible simulation. Okay, so in Stellarium, uh, Stellarium is a free planetarium software which you can use to predict when things will be visible, and it allows you to map out, for example, my tree line. And so I went through and I mapped out my tree line. And so with this program, I could tell when an object on any given night would clear the trees and know when it was about to be lost in the trees. And that gave me about a 3-hour window of shooting. So another important part of my planning process is, when do I start and when do I need to stop by? Here are the 3 telescopes that I used for many years set up on the driveway. The large telescopes have a pier that are on a very robust platform. Then I have a smaller scope that's on a lighter one. There's a laptop computer that you can see here that's driving them all. And then I have 2 fans here. This is done in August. And in early August, late July, if it's a wet year, we can have a lot of mosquitoes. So this is my anti-mosquito device. I would sit with this blowing in my face and they wouldn't bother me as much. Now the right gear. This is not my gear. This is my gear. And this gear was put together somewhat purposefully. Let's start over on this side. This platform is a 400 millimeter astrograph, and with that focal length, I can get about 2.5 degrees by about a 2-degree field of view. On the other end, I have a telescope with a focal length of 1085 millimeters, and that gives me about 1.25 degrees by 0.8. So just about half the field of view that this telescope gives me. The one in the middle, as it turns out, is 740 millimeter. That gives me a field of view of about 1.8 by 1.2, just about in the middle here. So these platforms were put together quite purposely so that when I'm picking my objects, I have to decide which telescope is the best fit for one that I'm going to be shooting. And in this particular case, for Messier 27, it's a smaller object. I went with my longer focal length telescope. This is an Astrophysics 130 millimeter Starfire EDT telescope. It was built back in 2003. Astrophysics is a very prestigious name in telescopes. Usually, if you want to buy one of these telescopes, you don't really have the opportunity to buy one. You put your name on a list. Sometimes there's a lottery. There are people who put an order in and wait 4 or 5 years before they get it. It turns out that when I bought my first telescope, I sold some camera lenses to pay for it. A gentleman who bought one of my camera lenses owned this scope, found out I was doing astrophotography. He tried to do it back in the 2000 timeframe, couldn't figure it out, never used it, and offered to sell it to me for a ridiculously low price, and I couldn't say no. But it's a beautiful set of optics. It's a little slow. It's an f8 system. It's a little slow, but it has amazing color and contrast. And for a very long time, this was my longest focal length scope. So smaller things tended to be slated to this scope for use. So we picked the platform. Now, how does this platform solve the fundamental problems of astrophotography? Well, we talked about the targets are small and faint. Well, the telescope helps with that. It acts as a light bucket. Basically, you have photons coming in at some flux rate, and it's a function of the objective area. The human exit pupil is between maybe 5 and 7 millimeters in size. Well, the scope is 130 millimeter. So that's a gain in area of 345x. You're now just basically funneling all the photons you can in this opening and concentrating them back on the sensor. So that's one way that you're helping with that small and faint problem. The other is because it's the longest focal length, it has the greatest image scale. That's about a magnification of about 22x. So the telescope helps in part of that. The other thing that helps is the cameras, right? There's a variety of camera types that are used in astrophotography. Some people just use straight unmodified digital SLRs. They take off the lens and mount the telescope with an adapter and use that. Um, there's also dedicated astro cameras, and they come in two flavors. This one is a one-shot color camera. That means it has a Bayer pattern on it, and every image that comes out is a color image. This is a mono camera. Often the same sensors, but they don't have the Bayer pattern on it. So every time you take an image, it's all one color. And if you want to have different colors, you put on a filter wheel here, which allows you to move with a motor any filter in front of the camera. And that's what we're going to be using for this particular project. And these Astro cameras tend to be cooled. The regular cameras are not, and that really helps with the thermal noise, which is a big issue when you're taking long exposures. So cameras capture photons, so they help with this fallen fate by the fact that they have a high quantum efficiency. The other also help because they can integrate flux over time, right? Your eye can integrate light over maybe an eighth of a second. I typically will integrate between anywhere from 30 seconds to 90 seconds for broadband exposure. Narrowband, where I throw away so much light with those tight filters, they usually go up to about 5 minutes. But that integration over time also helps. And when you think about it, I did the math at one point here on some of these faint objects. You might be getting 2 photons a second coming in. I mean, these are very, very slow flux rates coming into the scopes. So this is the camera that I use. It's a mono camera, has a 90% quantum efficiency, very low read noise. It has a deep electron well of about 50K electron volts. What this means is while I'm taking long exposures to build up the image of those faint nebulae, the stars are not faint at all, and they won't be overexposed because we have quite a bit of capacity to take a lot of electrons and store them up for the stars. The cooler can drive the camera down to minus 20 degrees from your ambient temperature. And so that really helps with the noise. And then with the filter wheel, you have a lot of flexibility on how you capture your color. So there's a camera, and this is the filter wheel attached in front of it. So let's talk about the filters for a second. Here's the top off of that filter wheel. And this one has room for 7 filters. There's my luminance filter, red, green, blue. And now you see there's a thicker filter in here. This is hydrogen alpha, this is oxygen 3, and this is my sulfur 2. So I have a combination of broadband filters and narrowband filters. Now, looking at them, this is the spectrum down in here, and you'd expect that the color blue is between 400 and 500 nanometers, green 5 to 6, and 6 to 7 is red. And you can see the cut of the filters, and they're pretty efficient. They go up to transmissions in the 90s, and they cut out those color channels. And these are very broad color channels, so it's pretty good for letting light in. The luminance filter spans that entire area, that black line there. So the luminance filter is letting in the most photons, and it gets the best exposure because it's not differentiating between color. Conversely, these narrowband filters, they can be anywhere from 3 to 7 nanometers in width. So they're very, very narrow compared to these, but they're lined up on very specific frequencies where the light excitation happens for these particular chemicals. And if you impose one on the other, you can see that's where oxygen 3 is falling in the spectrum there. Hydrogen alpha is over here, and sodium 2 is over there. I also have a plot on here of the quantum efficiency of the last generation of cameras. And if you look here, the peak efficiency was 60%. So now move that up to 90, and you get an idea how in one generation they've really improved things dramatically. The other thing we want to do is we want to keep things sharp, and we keep things sharp with a focus motor. Normally there'd be a knob here so you can focus your telescope. Instead, we have a pretty powerful stepper motor. But as the night gets colder, telescopes shrink and the focus changes, and you need to be able to deal with that. And the focus motor is really critical for making sure that happens. It's a high torque motor with very precision stepper counts that you can drive to. Very repeatable, holds the scope very rigidly at any given position. And used with control software, it can create an autofocus capability. So the way that works is when you do an autofocus routine, it sets a filter, backs the focus off by a certain number of steps, takes a picture, measures all the star sizes using a half flux radius metric, um, and then moves the focus in a little bit further and takes another image and does it again. And basically, you end up with a curve that looks like this. And at some point here, the size of the stars is the smallest you can get. And that's your point of best focus. You get your stepper motor count, and that's how you set your focus. Because this is automated, you probably do this when you first start up in the evening. You do it when you change filters. You can do it if it gets colder by 1 degree, it'll stop what it's doing and go focus. And sometimes I just do it every 30 minutes. Just, I don't know what could be going wrong, but I want my images sharp. So I'm going to pause and I'm going to do an autofocus run. This device is a camera rotator. It looks a little bit like a filter wheel, but its sole job is to rotate the camera. Remember when we talked about doing composition? Well, in order to do composition, you'd have to be able to rotate things. And this is what causes that to happen. So it's a precisely controlled motor, and it's very repeatable in its positioning night after night. And it knows it's very critical in its positioning because when it's in the position it thinks it should be in, it takes a picture with a camera, does plate solving, which looks at the sky and verifies what it's actually looking at, and corrects things so that you came back to exactly the spot you wanted. Okay, so now the Earth turns and we got to do something that tracks the sky, and that's the job of the mount. This is an Ioptron CEM60 mount designed for a 60-pound payload. We have 30 pounds riding on it right now. And basically, there's a big drive gear here and a worm gear in here that turns slowly, and that causes the whole thing to rotate at the same speed that the Earth rotates. And that's the main mechanism that we're going to use to make sure that we're compensating for that turn. And also, once you get it calibrated, it knows where it's pointing, and you can tell it where to go to, and it'll go to any part in the sky that you want to. So that's pretty nice. I've already covered that. Another thing is because this is a worm gear driven thing, you don't want a lot of weight. You don't want to stress the motor. So you spend a lot of time balancing the scope. These counterweights in these various positions are all set up so you can do 3D balancing so that the torque that the motor is dealing with is very minimal when it's really driving these scopes. Now, that drive has to be carefully aligned with the pole star, and that's the job of this particular device. Uh, it's called a pole master alignment camera. It mounts right on the main axis here. It looks towards Polaris, and it basically allows you to very conveniently adjust things so that you're in very precise alignment with the axis of the night sky as it turns. It's quick and it's easily done and it's very comfortable. And I have one of these on every one of my scopes. This is the thing that's going to also help me keep sharp images. This is my guide scope. It's a secondary telescope. It's a refractor. This one happens to be a Televue TV76. On the back is an imaging camera. And this combination monitors star positions within its field, and then it detects when those stars are changing position when relative to the sensor when they should not be. And it will send control signals to the mount to correct for that. Why would they change? Well, you're being driven by a worm gear and drive gear, and each of those teeth is milled and cut. And there's tiny variations in that, and that causes it to speed up or slow down based on how the gears are meshing. This monitors that precise process and nudges things to keep things in alignment despite the inaccuracies in the gears. All right, the night gets cold and we get dew. Well, we control dew by putting a strap around the element of the main telescope and the guide telescope. And this is a heating element. And this will, when it's needed, will heat up the element slightly, making it just a little bit warmer than the dew point, so dew never sits on there. So how do I know that? I have an environmental sensor here, which measures the RH and the temperature, calculates the dew point, and knows when to start sending energy and how much energy to these things to keep the dew off the objectives. Finally, we're going to control these things. And each telescope platform has a computer, and the computer is running software which manages the sequence of capturing images. It manages the equipment interactions, the collection of subframes, the tracking and guiding, and even when to do autofocus. Here is one such software. It's called Sequence Generator Pro. We talk about what gear is connected in the telescope. We talk about where we're going to be shooting we can come down here and we actually have the detail of each of the frames we want to capture, and I'll zoom in on that. You can have one, it's a light frame. You're going to use a hydrogen alpha filter. We're going to name the files with the hydrogen alpha name. It's going to be a 300-second or a 5-minute exposure. The sensor will be binned one by one, and I'll do it 20 times, then I'll move on to the next filter. And it'll control that sequence until you have all your images, and then it'll start collecting calibration frames down in here. So the setup, how do we set this gear up? Well, I'm setting up in the driveway for 3 telescopes each night. So in the daytime, I do the physical setup of the gear while it's nice and bright out. When it starts to get dark, I get the software all initialized and running. Then when it's dark, I do the polar alignments, I test the cameras, I cool the cameras down to their operating temperature, and I run the plate solver to calibrate the mounts. And then at that point, I'm pretty much ready to go. But I needed to do this setup more efficiently, and taking the telescope apart and moving it into place was awful. So a friend of mine designed this device that I call the telescope lifter and mover. He's a very talented mechanical engineer. He would probably have built this out of milled steel. I can't work with milled steel, but I can work with wood. So he designed something that even a dummy like me could build. But this thing will roll up to the larger telescopes. This will go under the base. This will cradle the column itself. There's straps that'll hold it on. Then there's a jack screw here on a carriage, and I use a drill to lift the telescope, and then I can wheel it around. And that makes things much easier because the telescope's all assembled in its final configuration. It's already balanced. I store it in the garage covered for dust. Then when I want to take it out, I wheel it out to the driveway and drop it on painted spots on my driveway so they're in a consistent position. And that's greatly assisted my setting up. So one night I did a setup and I realized I have a security camera in the driveway and it's motion triggered. And I thought, it might have taken pictures of me setting things up. Maybe I can do something with that. So I made this little video. So now we're getting ready to capture data. And with everything set up, I don't stay outside. I go back into my den and I have large computer screens and I do screen sharing with the laptops. And here's a night I actually captured the data for Messer 27, and you can see one frame of data there. You can also see the Propeller Nebula, which I'm collecting over here. And I'm not sure what I was collecting on that one, but I have 3 telescopes working, and I have a security camera that lets me look at the scopes from the inside, and also more importantly, listen. If something's not sounding right, I know something's gone wrong with the drive, so I better get out there. So let me just take it aside now. There's a lot of effort to make this easier and reduce the barriers for people who would like to get involved in this. There's a traditional method where you need to buy all these components, but the manufacturers are now making components that work well together. This item here, this item here, this item here, and this item here all come from the same manufacturer, and the software is very compatible. These other items come from different manufacturers, but they use a set of drivers that are compatible and they can cross operate. And so it makes it pretty easy to pull things together. And then microcomputers are available that run either software you purchase or software that is free that allow you to do these things. But there is a new trend starting for simplifying that. So what we're starting to see is these small turnkey devices. And probably the first one was the ZWO ASI Air. Instead of having a computer running generic software, this is a turnkey device. It has a computer in it. You can plug power in here, and on the other side, there's USB plugs to plug in. This will control everything. It's plug and play, and it uses Wi-Fi. You talk to it with your smartphone, and you have a very polished app that allows you to control the process. And this makes it very simple. The downside of this is that it only works for devices from this company. StellarMate is a similar device, which is kind of a turnkey operation, but they're more agnostic. You can use just about everyone's devices on it. But they're still trying to find clever ways to do even more. And ZWO just came out with this new camera, which is pretty interesting. It's a regular camera. It has one sensor. Then it has a guide sensor in it, and it peels off a little light from the main telescope. So while this is imaging, This is doing the tracking. And the functionality of this computer is built into the camera itself. Things plug into the camera, and then it has Wi-Fi you can connect with your phone. So they're starting to create ecosystems that make it easier for you to hook these things together and run things. Going to the real extreme, we now have these smart computers. These smart computers are a combination of camera, focuser, mount, computer, focus motors, filters, all in one integrated smart package. They even do automated image processing with progressive tracking by or progressive stacking. And what I mean is it'll take one picture, say 10 seconds. It'll show you that picture and it's pretty blah. Then it'll take a second one and it'll add it to the first one. And the picture starts getting better. And every 10 seconds, it gets better and better and better. And after a minute or so, you're starting to see what's happening there. So it's good for a real-time experience. It's also good for imaging. And you don't have to know a lot. You set these things down. Usually you have to level them, and then they're smart enough to set themselves up, look at the sky, and do what they have to do. ZWO Star 50 runs for about 500 US dollars. And I actually own this one. Dwarf Labs Dwarf 3 is another unit. It's about the same price range, a little bit more. A new one that's just come out, and I don't think they've actually delivered them in the field yet. Celestron has this smart telescope, which this is a serious telescope. This is a 6-inch Cassegrain. I think it's like an F2 system on a precise mount. So it's $4,000, but now you're getting into very capable systems that have much greater ability, not limited by the cost that you see here. So what's my take on these new devices? You know, they're going to automate all this and take all the fun out of it. Well, I have to say these small systems are a boatload of fun. I don't have one myself. I enjoy using it. I enjoy using it to show this guide to my kids and friends and their kids. So I get a lot of enjoyment out of it. Even the low-cost units are fairly sophisticated in what they can do. When they're used as designed, they can create reasonably good images without a whole lot of learning on your part. So that's pretty nice. Many people go beyond what they offer to get even better images. They add equatorial adapters, they doctor it so they can get longer exposures, and then they take all of the images captured and do their own processing. This sort of gets away from, the simple system to use, but people are trying to maximize what they can get out of it, and they're having some success. Most of the lower cost units they're constrained. They're relatively low resolution. There's no cooling. The exposures they can take are very short, maybe 10 seconds and no more. So they're kind of limited in their current form. More expensive units are starting to show up that kind of address these shortcomings. So I should mention, this was a picture of the moon I took with my sea star there, so it can do a nice job of that kind of thing. Here's what my phone screen looked like using it when I was trying to get Messier 31, but it was so big it didn't even fit in the field of view. And last year's C2023 Comet, which had the antitail, I was able to image that with it while I was on vacation. I don't know if it shows up in this, but there's a real hint of the antitail there. I have a suspicion that you guys probably can't see it with this kind of a projection. But, in my mind, these are great for exploring the skies, introducing people to the sky. You see things visually through these that you can't see with a telescope because they integrate over time. And for people who want to start playing with astrophotography and they don't want to take it so seriously, they have to learn a lot of stuff. It's a way to get your toe into the water and see if you're really interested to pursue it. But if you're going to create high quality astro images, you need more than these can deliver right now, right? Ask me again in 2 years, that could change. But right now, what it takes to really deliver a great image, you have to go beyond almost every dimension of what these can do. So let's talk about the capture. So when we start this thing up, the telescope slews to where the object is in the sky. It does an autofocus series, then does this plate solve so that it knows that it is actually looking at the part of the sky it's supposed to be looking. Then it starts the guider. Then it starts capturing the first batch of sequences. When it's done with that, it moves to the next by changing the filter. Keeps doing that until it's done with what you told it to capture it. And then it'll go through and you can do the calibration exposures. Now, the software will tell you what it's trying to shoot, when it's going to start, when it's going to end, what its steps are to get there. And as it does each step, it'll give you some kind of real-time feedback of what it's doing. So as it's doing it, you have some idea of what's going on or if something's going wrong. And it'll tell you that and it'll get your attention so you can step in and help. But we also have something called flats. And flats are an evenly illuminated field. I'm using a LED tracing panel, and we take pictures of that, and it characterizes some optical elements of the telescope. The vignetting flats allow you to take a picture of a evenly illuminated field, and that allows you to document the characteristics of your optical system. And the two things it's fundamentally going after are the vignetting that's natural in all optics and any kind of unresolved dust, out of focus dust that might be on the sensor window, it might be on the filter glass, and if it's there, it will cause a slight distortion. And with flat calibration, you capture the data, it allows you to subtract that off and completely eliminate that problem. So it's a very important thing. Now, because I move my telescopes around, and this documents dust, when you think about it, if your dust is being bumped because you're moving the scope, one night it might be in a different position than another night. So that forces me to take these flats every night I shoot, because when I put the telescope away, I might be jostling the dust and it might be a different pattern. So I have to calibrate my images on a nightly basis for that reason alone. All right, the final data set. When I went after this project, I ended up shooting on the nights of August 2nd, 3rd, and 4th of 2022. I only shot those nights because it was cloudy for weeks after that. I lost my opportunity to go deeper. I ended up getting about 10 and a quarter hours of subs, and you can see how many I got in this particular configuration here with each of the filters. And then I had cal frames. I had 30 darks at 300 seconds, which was my exposure time. And then for each night, I had a set of flats and darks for the flats that went with that. When I got done with the project, I had 378 image files that I now needed to combine. And one of the things you typically do is you look at each one of these files because maybe something went wrong. Maybe a cloud moved in and you don't want to use that image. And I have a video here, which probably I'm thinking isn't going to play, that shows what that looks like. Let me try this again. Oh, this one looks like it is playing. I don't know why the other one did not. You'll see the image is jittering. That's purposeful, and I'll talk about that in a second. But what you didn't see is there was an airplane that went through one of those frames. They must have hopped over that frame when it was playing. The jittering is done on purpose. Every time we go to do another frame, the mount just jostles the positioning a little bit. That allows the image to fall on different pixels and different pixel breakpoints so that you can actually synthesize a higher resolution, because maybe it's all contained on one pixel or maybe it's split through a pixel, but if you move it around a little bit, it actually helps your imaging. So that was on purpose. But you'd go through this and you might have an image where, you know, clouds moved in. You got to call those images out. They're not good data. They're not going to help you. So you typically go through all the data looking for something that might have gone wrong. So now we got to combine all this data together. And I built a computer that would work on all this data. This is a 12-core, 24-thread computer with lots of power and lots of memory so that it could really crunch the data and do it in a timely fashion. And the pre-processing, the task is we're going to combine all those subframes and cal frames to create a master image for each filter. Sometimes you hear this referred to as stacking, but it involves a lot of things. We do cosmetic correction, which is looking for hot pixels and bad pixels in the sensor, and we fix that. We calibrate and normalize each of the images to the calibration frames. We do image registration so that each image is lined up where it should be relative to the other images. Then we integrate them together, and when we integrate them together, we also reject pixels that look bad, and we'll talk about how we do that. The stacking process reduces the noise and enhances the signal. The signal to noise improves based on the square root of the number of frames. So we got about 40 frames. So we got about 6.3 times better signal to noise because we had that sample. If I want to double that to go to 12, we need to do 12 to the second power. We'd have to step it up to 144 frames to get double that. So each time you have a doubling, you have to dramatically increase the size of their sampling. So what are we capturing on these images? One thing we capture is bias noise. That's the electronic noise that's generated by the A to D converter for every pixel. And we have hot pixels, which are causing a certain level of noise. Then we have dark current noise. If we're having a 300-second exposure, that chip is operating for 300 seconds and it's electricity going through it. It's generating thermal energy, and that's creating its own set of noise, and that stacks on top of the bias noise. You also will have amplifier areas of the chip that generate more heat, and they can sort of bleed over into pixels that are close by on the chip, and they call that amp glow. Then we have the flat signal we talked about, the optical vignetting, as well as dust and stray particles. And finally, we have light that's coming in the telescope. And you'd like to think all that light's coming from your target for the evening, but you're getting light from light pollution, atmospheric glow, and from your astronomical sources. And what we want to do in calibration is we want to take dark calibrations to remove this from the signal. And then we take flat calibrations, which remove that, and hopefully just leave the light signal itself. So we have a stack of images going to make a master image. Think of it this way. Imagine you picked a pixel, and now in this stack, you might have 30 or 40 samples of that pixel. You can make a distribution of that, and if all you did was just average everything, you'd get a better pixel and better noise. But because there's a distribution here, what happens is things that look the same on every frame get reinforced. Things that are odd in one frame and not seen anyplace else will get diminished. And so that statistical process can be used to do pixel rejection. So I talked about the airplane pixels going through your frame. I really wouldn't throw that frame out. Instead, we realize that those pixels don't look like this distribution, and there's a statistical process that will automatically reject those pixels as we integrate things together. So here's a raw subframe, and when you look at it, you can see hot pixels, and you can see noise, and you can see a little bit of structure in there. Once we integrate that, suddenly we're seeing a lot more detail and structure, and the noise is a little bit better, and we've gotten rid of our hot pixels. And this is the kind of improvement you're trying to get when you try to stack things together. So this is where I'm speaking from right now. This is my Astro Man Cave, and this is my image processing station. And this is where all that work happens. At the end, you end up with a master image. This is the master image for the hydrogen alpha. Impressive, isn't it? I think the only thing I see on here is a couple of stars. So what went wrong here? Well, this is the statistics for that image. There's 25 million pixels in there. And these, I should mention, these pixel values have been normalized between 0 and 1. So we have a maximum signal in there of 0.99. We have a minimum signal in there of 0.00005, which that's our noise floor. And we have a mean that's above that. So there's something in here, but I'm not really seeing it. Well, when you look carefully, you can see this orange line here at the very end of the curve. Well, that's most of our data. Now, there are some stars scattered across this, but almost all of our data is shoehorned down on the low end of the curve. This is a 16-bit sensor, and we're way down in here. So let's zoom in a little bit. Oh, there's our data. This is our noise floor right here, and this is all the data that we've gotten from the nebula that we're shooting. While there's a little bit of coming from the stars themselves, the signal is really pushed way down here. So in order to even see this, you have to stretch the image a lot. And we don't want to stretch the image now because we're going to be operating on this data to clean it up even more. So what we do is we have a screen transfer function. So that scales it up for what's displayed on the screen without touching the actual values of the original pixel. And when you do that, you can now start to see what you get. You get your linear masters. And let's just take a look at the linear masters for a second, because I found this fascinating. In hydrogen alpha, look at the shroud around here. It's delicate, like a lacy pattern with a lot of structure and detail. Then we go over to the oxygen signal, and notice how smooth this is. It's very smooth and without a lot of structure and detail. Almost looks like, butterfly or angel wings or something. But in sulfur, we really see what the original image looked like. We don't see any shell out here. There's no gas in there. Most of the sulfur is inside of here. So we got 3 very different looking images depending on what molecule we were imaging on. Now the question is, how do you combine these together to form a color image? Well, there's a standard method called the Hubble palette, because the Hubble telescope does it. And that takes the sulfur image and maps it onto the red. It takes the hydrogen onto the green and the oxygen onto the blue. And that can create a very pleasing mapping. But there are others. So here is the Hubble view of that data. Here is another view where we basically said, I've got so little sulfur data, I'm going to throw it away, and I'm just going to use the oxygen twice, and I'm going to put the hydrogen data in the red. And sometimes people do blends of them to make different details pop out. Red could be a combination of those three channels in some way. So it's false color. You can do anything you want to do. For this project, I chose to go with the Hubble palette. So the first thing we want to do is we want to clean up the pixels even more. As you get to the edge of the field, these stars are no longer round. They're kind of egg-shaped. That's aberration. And there are tools that allow us to correct that. And once they're corrected, the stars are now nice and circular at the edge of the field. And that just makes things better before we start processing them. Another thing is that there's so many things which are acting to defocus the data you captured. Your optics aren't perfect. You have wind, you have the turbulence in the sky. Everything acts to defocus it. And interesting thing about astrophotography is we have a way of measuring that defocusing, because in theory, each of these stars is one single pixel in size. They're true point sources. But if we measure that, we can measure the size and the shape of that size, and we can characterize the way this was defocused by the optics and the environment. And because we have these probes in here, we can actually do something called deconvolution, which is not a sharpening step, it's a sharpness restoration step. There's new AI versions of that which do it even better. So we can go from an image like this to an image like this, and you notice the stars are much crisper now, and the level of detail and sharpness has been improved a lot because we took out the level of sharpness loss that we were able to characterize. We also have a lot of noise we're going to deal with, and we have AI tools which have gotten very good at dealing with the noise. And I always leave a little noise in because I think the images look more natural with a little bit of noise without going too far. But it really helps a lot because you're always fighting the signal and noise. Another thing I tend to do is I create a lot of masks. Masks are basically black and white images that allow you to focus processing steps on certain portions of the image. So for the hydrogen alpha, I've created a mask which covers the entire object, but I have one that just looks at the outside, and I have another that looks at just the inside. And I can do the same thing for oxygen 3, and I can also do it for the sulfur in here. This allows you to do very focused processing, and so use of masks is very common. And when we do the image processing, I'm not going to go through this in a lot of detail, but you basically end up with the master images are combined to color, where I do some operations. Then they're split apart, and I really want to emphasize the detail in each of these channels, including using masks to enhance them further. Then I create a color image, which is processed with the goal of having the best color and low noise. Then I created a synthetic luminance image by combining together those images. And I process this for sharpness and detail. And that ends up creating two very different images, which I combine to get the final image. And so I go from a starting image that looks like this to my final image, which looks like that. So this is what most people have seen. This is the image I came up with, and I was very happy that I had achieved my goal. I really was able to capture a lot of detail in here. And some of the detail I didn't even understand. I didn't understand why there's these black lines coming out, but it was kind of cool. And I thought this was a good image, but is this an image that other people would consider good? And one way that we gauge ourselves, we submit this to publications and see if anybody will publish it. And it's pretty hard to get something published because there's lots of people doing this. But as it turns out, this image was selected for Amateur Astronomy magazine in the April issue of 2023. In May, it went into Astronomy magazine. It finally went into NASA APOD. Now, NASA APOD is Astro Picture of the Day. And NASA picks one image, which is, it thinks, the most impressive image to put up. And it's choosing from images from the Webb telescope, Hubble telescope, professional observatories. And when they put it up, they have a professional astronomer analyze and talk about what you're looking at. Then they have a chat room where people, other astrophysics folks, will debate what they're seeing there. And for the first time, my image got chosen for that. So it was very interesting to see them discussing these dark lines and have them theorize that these red dust clouds were stopping the energy from the core to getting to the gas in here. So this gas was excited by energy from the central star, and this was masked. But it was kind of neat to get into the NASA list. It was in Sky at Night magazine in August, and Sky and Telescope published it in September of that year. So this is the first time I submitted an image, and it was published every place that I submitted it. So that's kind of a grand slam. So for me, that was something that said this was a special image. It was a great image. I've never had another image that did that. I hope someday I will, but you never know how these things go. Sometimes it takes a lot of skill. Sometimes it's a little bit of luck, and depending how people respond to it. So what makes for a great astrophoto? Well, planning, right? The right target, good composition, unique imaging goals, and the right capture approach to meet those goals, which is no different than any form of photography, correct? The right timing, making sure it's placed well in the sky, you have good conditions, you have clear nights, no moon, you can get the data. The right gear, the gear is configured to best meet the needs of your goals for imaging. It's high quality, well-performing gear so that it's working the way it should, and you're doing the right kind of capture with a good camera and the right kind of filters. And then there's technical excellence, great capture with long integration times, solid autofocus performance, and good tracking. The gear's behaving itself. It's not losing its mind and going crazy in the middle of the night. Good data preparation, inspection, and filtering. The proper calibration data was collected. Great stacking, that everything was put together to create the best possible master images. And that results in images with tight, small stars with good color, great signal to noise ratio, excellent sharpness, and good signal levels, for your target. Then it comes down to image processing. And this is where the art comes into it a bit. It's a valuable skill set. It is more art than science. Every astrophotographer has his own look. If I gave the same data set to 10 astrophotographers, I'd end up with 10 excellent but very different looking images. You don't want it to be over-processed or under-processed. You want a natural look. And experience plays in this. You have to do a lot of bad images and have the experience of creating those bad images before you start getting better. And developing your own mind's eye and knowing how you want your images to look, that's important. Sometimes it's just plain luck. It can be hard to predict what will resonate with other people. I think often what happens is it's a summation of a lot of tiny optimizations, but by themselves may seem unimportant, but taken together across the whole imaging chain really help to create an excellent astro image. So some of it is science and some of it is art. And the bigger part that I'd like to admit sometimes is the art. So that's pretty much concludes my presentation, but I did want to do a quick segue is that I'm making a bit of a change. I am upping my game, and I've just completed a 3-year project where I have built my first observatory. I'm calling it the Whispering Skies Observatory, and I wanted to just share that with you as a way of wrapping up this talk. I'm running along. I'm going to cut that short, but that gives you an idea. It's a 16-foot by 20-foot observatory with the ability to roll off a roof. I have 4 piers in it. I've now expanded it to 4 telescopes that I'm doing. I no longer set up in the driveway, which is great. And this is what it looks like when the roof is closed and everything's protected from the weather. It only takes me a few moments to open the roof and get ready to start shooting. And I now have yet another telescope, which is a galaxy scope. This is a 1300 millimeter focal length f5 system that lets me go after those small galaxies even better than I could before. So this is very new. Just in the last 2 weeks, I've had my first light from the observatory, and I'm excited to enter a new chapter. So with that, I thank you for your patience and putting up with my long-winded discussions of astrophotography. I hope you found some interest and some interesting tidbits in there about what it's like to try to go after the deep sky.